Reality itself might be playing a trick on us. At the smallest scales, particles behave in ways that defy common sense, appearing to change their very nature just because someone is watching. This is not a minor scientific quirk, but a deep crack in the foundation of what we think is real. To solve this, physicists have proposed one of the most radical ideas in all of science: the many worlds interpretation. It suggests a breathtaking answer that every possible outcome of every quantum event actually happens, spinning off into endless alternate realities. By the end of this exploration, you will understand how this controversial theory attempts to rebuild our concept of the universe from the ground up. We will uncover what it means for your own identity and question whether we are truly alone in a cosmos of infinite copies. What version of reality feels most true to you? This central puzzle is known as the quantum measurement problem, and it asks a deceptively simple question: what exactly triggers the shift from a fuzzy cloud of possibilities to a single, definite result? The dominant answer for most of the last century has been the Copenhagen interpretation. It says that a particle exists as a wave of probability, described by its wave function, right up until the moment it is observed or measured. At that instant, the wave function collapses and the particle snaps into one specific location or state. But this explanation raises more questions than it answers. What qualifies as a measurement? Is it a conscious human mind, or can a machine do it? And what physical process actually causes this sudden, mysterious collapse? There is no equation for it. It is simply a rule added to the mathematics to make the theory match what we see in our labs. To truly feel the strangeness of this, we need to look at the experiment that exposes it most clearly: the double slit. Imagine a barrier with two thin, parallel slits cut into it. We fire tiny particles like electrons, one at a time toward this barrier. If electrons were simply little bullets, we would expect them to go through one slit or the other and build up two piles on a detector screen behind the barrier. That is not what happens. Over time, each individual electron lands as a single dot, but as thousands of dots accumulate, they form a pattern of light and dark bands. This is an interference pattern, the unmistakable signature of a wave. It is as if each electron passes through both slits simultaneously, like a wave of water would, and interferes with itself on the other side. Now here is where the mystery deepens. If we place a detector at the slits to see which one each electron actually goes through, the pattern on the screen changes completely. The beautiful interference bands vanish, replaced by two simple piles. The act of measuring the electron's path seems to force it to behave like a particle. According to Copenhagen, our observation collapsed its wave function. It went from being a spread-out probability wave going through both slits to being a definite particle going through just one. This is the heart of the measurement problem. The mathematics of quantum mechanics describes the electron perfectly as a wave until the moment of measurement, and then that description abruptly, mysteriously stops. The observer appears to play a privileged and unexplained role in shaping reality itself. For many physicists, this is philosophically unsatisfying. It places a fundamental limit on our description of the world, suggesting there is an unbridgeable gap between the quantum realm and the world we experience. The stage is now set for a truly radical alternative, one that proposes a universe where the wave function never collapses at all, because there is no need for it to. Into this philosophical stalemate stepped a brilliant and unconventional graduate student named Hugh Everett III. In 1957, while working on his doctoral thesis at Princeton, Everett asked a question that seemed almost childlike in its simplicity, yet devastating in its implications. What if the wave function never actually collapses? What if the mathematics of quantum mechanics, which describes all those probabilities so perfectly, is telling the complete and literal truth about reality? His radical proposal was this: the wave function does not collapse because every possible outcome contained within it physically occurs. When an electron faces those two slits, it does not choose one path over the other. Instead, the entire universe splits. In one newly branched reality, the electron goes through the left slit. In another, perfectly real and separate branch, it goes through the right. The interference pattern we see is not a ghostly wave, but a record of these branching histories overlapping before they fully separate. Everett's motivation was pure elegance. He sought to remove the arbitrary, unexplained division between the quantum world and the classical world of everyday experience. In his view, there was only one set of rules, the seamless, continuous equations of quantum theory, applying to everything from a single electron to the entire cosmos. There was no special role for measurement or observation. The universe was simply a vast, evolving wave function, and what we perceive as a single history is just one thread in an endlessly branching tapestry. He presented this idea, which he called the relative state formulation, to the towering figures of physics. The reaction, particularly from the aging pioneer Niels Bohr, whose Copenhagen interpretation had become orthodoxy, was dismissive at best. The establishment saw it as philosophically extravagant, a violation of common sense that multiplied realities beyond necessity. Disheartened by the cold reception, Everett soon left academic physics behind, pursuing work in defense and operations research. His revolutionary thesis gathered dust, a brilliant but neglected idea that seemed destined for obscurity. It would be other thinkers, decades later, who would rediscover his work, rebrand it the many worlds interpretation, and begin to grapple with its staggering consequences. The theory's genesis is a human story, a reminder that even the most profound insights about the cosmos can emerge from a single mind questioning what everyone else accepts as fact. Everett's proposal is disarmingly straightforward. He took the central equation of quantum mechanics, the one that describes how a wave function evolves smoothly and predictably over time, and decided to believe it completely. This equation, known as unitary evolution, has no provision for collapse. It never stops, so Everett asked, what if it simply doesn't? What if the wave function, containing every possible future for a particle, just keeps expanding forever? The many worlds interpretation is the logical answer. It states that every single possibility encoded in that wave function is realized. The universe does not choose. It branches. Think of it not as one reality splitting into two, but as a single, ever-widening river of possibility. At every quantum event, every flicker of uncertainty, the river forks into countless new channels. Each channel carries forward a complete and consistent version of history, one where a specific outcome happened. In one channel, the electron in our experiment went left. In another, it went right. Both are equally real, both are equally physical. They are not parallel universes in some distant, separate place. They are right here, superimposed upon one another, but forever diverging. We do not perceive the branching because we are carried along within it. From inside a single channel, you only experience the sequence of events that defines your branch. The you in the other channel has an equally valid but now separate experience. This solves the measurement problem with breathtaking elegance. There is no mysterious collapse because nothing ever gets discarded. The observer is not special. They are simply a complex collection of quantum particles that become entangled with the system they are measuring. When a scientist looks at the detector, they do not cause a single result. Instead, their own quantum state becomes linked to the outcome. The total wave function branches to include a version of the scientist who saw the electron go left, and another, fully real version who saw it go right. Both exist, The randomness we perceive is an illusion, a consequence of our limited, single-branch perspective. We are like a character in a book who can only read one sentence at a time, unaware of all the other possible paragraphs the story could have contained. The entire branching multiverse is the book, but if the universe is constantly branching, why do we experience a single, solid world? The answer lies in a powerful and essential process called decoherence. This is the missing mechanism that transforms the abstract mathematics of many worlds into the tangible reality we perceive. Decoherence explains how the ghostly superposition of possibilities, like an electron being both here and there, gives way to the appearance of a single, definite outcome for any observer within a branch. It is not a collapse but a fading from view. Think of a pebble dropped into a still pond. At first, the ripples are clear and coherent, spreading out in perfect, overlapping rings. This is like a pure quantum superposition. Now imagine the pond's surface is suddenly disturbed by wind and rain. The clean ripples become lost in a chaotic jumble of waves. You can no longer trace the original pattern. The information about that specific ripple has leaked out into the vast environment of the pond. Decoherence works in a similar way. A quantum system, like Schrödinger's famous cat in its box, is never truly isolated. It is constantly interacting with its environment, even if that environment is just a few stray air molecules or the faint glow of background radiation. These interactions are a form of measurement. Each air molecule that bounces off the box becomes entangled with the state inside. Is the cat alive or is it not? The molecule carries away a tiny piece of that information into the wider world. Multiply this by trillions upon trillions of interactions with photons, dust particles, and the very atoms of the box itself. In an instant, the superposition of a live and dead cat leaks out, spreading irreversibly into the environment. From the perspective of any one branch, the other possibility becomes inaccessible, lost in a sea of quantum noise. It is not that it ceased to exist. The other branch of the wave function with the opposite outcome continues on its way. But for you, trapped within your specific chain of entanglements, the world now appears classical and definite. The branching was not a sudden, magical event. It was the inevitable result of quantum information spreading at the speed of light, a natural consequence of entanglement on a cosmic scale. Decoherence provides the how, turning the philosophical idea of many worlds into a rigorous physical process. It tells us that our experience of a single reality is a local phenomenon, a quiet backwater in a raging multiversal river. The multiverse is not a gallery of distant, finished worlds. Its true structure is far more dynamic and organic, best imagined as an infinite, ever-growing tree. The trunk represents the initial conditions of our universe at the Big Bang. As time flows upward, every quantum event, every flicker of possibility, becomes a fork in the branches. Each split creates new, real timelines that diverge and grow apart, never to reconnect. Your life, your history, is a single pathway climbing one specific branch of this colossal tree. But for every choice you made, a version of you exists on an adjacent branch where the opposite decision unfolded. This is not about traveling to a different planet, but about recognizing that all possible histories are woven into the same fundamental fabric of reality, perpetually branching from the same root. This model helps us move beyond the science fiction image of parallel Earths floating in some other dimension. Those stories often treat alternate realities as stable, complete places you could visit. The many worlds picture is more fluid and immediate. The branching happens here and now at every moment, driven by the fundamental randomness of particles. The difference between you and your other self on a neighboring branch might be as trivial as the spin of a single electron in a distant star, a difference that occurred a billion years ago and has since cascaded into a vastly different present. Our universe is not one thread in a static tapestry, but one strand in an endlessly proliferating weave where new patterns are born with every quantum heartbeat. This perspective forces a profound shift in how we view possibility. Nothing is merely potential. Everything that can happen does happen somewhere on the tree. The version of you that won the lottery exists. So does the version that took a different route to work this morning. The tree holds every tragedy averted and every opportunity missed, not as ghosts but as full physical realities. This can feel overwhelming, even unsettling, because it challenges our deepest notions of self and destiny. If every possible version of me is real, what makes this particular me, the one experiencing this moment, fundamental? The answer, according to the theory, is nothing and everything. You are fundamental to your branch, a unique observer experiencing one coherent stream of events. The others are just as real, but they are now separate stories in the multiversal library. This leads us to a question that tests the very limits of identity. If all these versions spring from the same source, at what point do they stop being you? The sheer scale of this branching is almost impossible for the human mind to grasp. It forces us to ask a direct and staggering question. Does every single flicker of quantum possibility, every tiny event at the subatomic level, truly spin off an entirely new universe? According to the strict logic of the many worlds interpretation, the answer is yes. Branching is not a rare cosmic event. It is constant, relentless, and woven into the fabric of existence itself. Every time an electron's path is not determined, every time a particle could decay or not decay, every quantum interaction with more than one possible outcome becomes a fork in the road. The universe does not pause to decide. It takes every path. To put this into perspective, consider a single atom in the air around you. Its electrons are not neat little planets orbiting a nucleus. They exist as probability clouds, and their interactions with light, with other atoms, with the very fabric of space, are fundamentally quantum events. Each of those interactions presents multiple possibilities. Now multiply that one atom by the trillions upon trillions in just the page of a book or the screen you are looking at. Expand that further to every atom in your body, in the earth, in the distant stars. The numbers become not just large but truly infinite. Physicists who support the idea estimate that branches are splitting from one another at a rate of trillions upon trillions every nanosecond. It is an explosive, exponential flowering of reality happening far faster than the speed of thought. This is what philosophers call an extravagant ontological commitment. It means the theory asks us to accept the existence of an unimaginably vast multiverse as the price for a simpler, more elegant set of underlying equations. It trades the mystery of wave function collapse for the breathtaking, and to some, overwhelming reality of infinite copies. Your life, in this very second, is not a single thread. It is the trunk of a tree that is splitting into more branches than there are atoms in the visible universe, with each new branch giving rise to its own endless cascade. A version of you just inhaled a slightly different arrangement of air molecules. Another version experienced a different pattern of photons hitting their retina. Most of these branches are nearly identical, differing by quantum events so insignificant their effects may never be noticeable. But given enough time, those tiny differences can compound, leading to branches where history itself unfolded in profoundly different ways. The weight of this idea can feel immense as it redefines not just the cosmos, but the meaning of every moment. It suggests a cosmos of boundless potential, where nothing is ever truly lost, only separated. This infinite branching forces us to confront a deeply personal question. If countless versions of me are being spun into existence with every passing moment, which one is the real me? The many worlds interpretation does not just reshape our picture of the cosmos, it shatters our traditional understanding of identity. in a universe of endless copies, the very idea of a single, continuous self begins to dissolve. You are not a unique soul on a solitary path. You are a pattern, a specific arrangement of information and memory being instantiated across a vast forest of branching timelines. Each copy, from the moment of a quantum split, begins its own separate journey, accumulating its own unique experiences. The you reading this sentence and the you on a branch where you decided to skip this video are both equally valid, both equally real continuations of the person you were a minute ago. They simply inhabit different, now disconnected, stories. This resolves a major criticism of the theory, the puzzle of probability. If everything happens, why do we observe some outcomes as common and others as rare? Why does a flipped coin land heads half the time, instead of in a universe where it always lands heads? The answer lies in what physicists call subjective probability. Imagine 100 identical experiments are about to measure a quantum particle. According to the wave function, there is a 70% chance of result A and a 30% chance of result B. As the measurement happens, the universe branches. In 70 of the new branches, the scientists observe result A. In 30 branches, they observe result B. Crucially, from inside any single branch, a scientist has no access to the others. They simply record a single outcome. For the scientist in a branch, it feels like they witnessed the 70% probability play out correctly. For the scientist in a B branch, they feel they witnessed the less likely 30% outcome. Both are correct from their subjective viewpoints. The probabilities we talk about in quantum mechanics do not describe the chance of something happening, but rather the measure or proportion of branches in which that outcome occurs. You are more likely to find yourself in a branch matching the higher probability, simply because there are more copies of you there to have that experience. This elegant solution ties our perception of randomness directly to the branching structure itself. It means that your conscious experience is always locked to a single, linear thread within the multiversal tapestry. You are not aware of the splitting, only of the consistent history of your own branch. This leads to the final, and perhaps most mysterious, frontier of this idea. What is consciousness in such a cosmos? Is it a process that somehow picks one branch to inhabit, or is it, like everything else, simply a physical pattern that is duplicated with each split? The theory suggests the latter. There is no special seat of awareness that jumps between timelines. Each copy of your brain, each identical configuration of neurons holding your memories and thoughts, wakes up into its own separate stream of moments, each convinced it is the only one. This is a humbling and expansive vision of existence, where every possible thought, every path not taken, is lived out in full. This dizzying vision of endless selves leads to a powerful thought experiment, one that pushes the idea of observation to its absolute limit. It is called Wigner's friend, and it asks whose measurement truly counts. Imagine a physicist, we will call her Alice, inside a sealed laboratory. She is about to perform a classic quantum experiment, perhaps measuring the spin of an electron. Outside the lab stands her colleague, Eugene Wigner. From Wigner's perspective outside the door, the entire lab, including Alice and her equipment, is one big, unmeasured quantum system. So here is the paradox. Alice performs her measurement. She sees a definite result, say, spin up. For her, inside the lab, the wave function has collapsed. The experiment is over, but for Wigner outside, who has not yet looked, the lab is still in a superposition. From his point of view, Alice herself has become entangled with the electron. There is a version of Alice who saw spin up and a version who saw spin down, both existing in a ghostly blend inside the sealed room. Only when Wigner finally opens the door and asks Alice what she saw does he force a single outcome for himself. So who is right? When did reality actually become definite? For Alice, it happened the moment she looked at her detector. For Wigner, it happened only when he observed Alice. This creates an infinite regress of observers. What if Wigner's friend is outside watching Wigner? When does the chain of observation finally end? The Copenhagen interpretation stumbles here because it cannot define what qualifies as a true observer. Is it a machine, a cat, a human, a conscious mind? It introduces a mysterious boundary between the quantum and classical worlds without being able to say where that boundary lies. The many worlds interpretation cuts through this knot with a single, elegant slice. In this view, there is no chain of observers waiting for a final collapse. There is only continuous branching. When Alice measures the electron, she does not cause a collapse inside the lab. Instead, she becomes entangled with the outcome. The total wave function branches to include an Alice who saw spin up and an Alice who saw spin down. Both versions are real, but they are now decohered, separated. From inside each branch, each Alice has a perfectly definite experience. Now, when Wigner later opens the door, he is not causing anything to collapse either. He is simply stepping into an already branched reality. He becomes entangled with the Alice he encounters. In one branch, Wigner meets the Alice who saw spin up, and they agree on that result. In another, equally real branch, he meets the Alice who saw spin down. There is no paradox because there was never a single shared reality waiting to be resolved. Both sequences of events, Alice seeing up then telling Wigner, and Alice seeing down then telling Wigner, unfold completely in parallel. The branching happened at the first interaction, and everything that followed, including Wigner's observation, was just more detail being woven into each separate timeline. This eliminates the need for a privileged first observer. In many worlds, every interaction is just more branching, more entangling. The universe does not care if the observer is a human, a computer, or a piece of photographic film. All are physical systems governed by the same quantum rules. What we call a measurement is simply the point where a quantum possibility becomes so widely entangled with the environment that it becomes irreversible from our local perspective. Wigner's friend is not a paradox for this theory. It is a confirmation of its core principle, that reality is not a single story waiting to be read, but a library where every volume is being written simultaneously. Schrödinger's famous cat was never meant to describe a real animal, but to expose the absurdity he saw in the prevailing interpretation of quantum theory. He imagined a cat sealed in a box with a fiendish device, a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers, releasing the poison. According to the Copenhagen rules, until someone opens the box to look, the radioactive atom exists in a superposition of decayed and not decayed. This means the entire system, including the poor cat, is suspended in a ghostly blend of alive and dead states. The act of observation alone is what supposedly resolves this gruesome uncertainty, forcing the cat into one fate or the other. The thought experiment was a critique, highlighting how applying quantum weirdness to everyday objects leads to a conclusion that feels monstrous and illogical. But through the lens of many worlds, the paradox vanishes and its meaning transforms entirely. In this view, the cruel suspense never happens. The moment the radioactive atom interacts with the Geiger counter, a definitive quantum event occurs. The universe does not wait for a human observer. It branches. In one newly created reality, the atom decayed, the poison was released, and the cat has passed. In another, equally real and separate branch, the atom did not decay, the vial remains intact, and the cat is alive and well. There is no superposition of a half-alive, half-dead cat. There are two real cats in two real worlds, each following a clear, consistent history from that pivotal instant. The observer who later opens the box does not cause a collapse or determine an outcome. They simply step into one of these pre-existing branches. They become entangled with the result, meeting either a living cat or discovering a loss, but they do not create that reality through looking. This reframes the entire thought experiment. It moves from a story about the mysterious power of observation to a profound statement about the structure of existence itself. Reality is not a single narrative hanging on our glance, but a forking tree where every possible storyline is written in full. The emotional weight shifts from the imagined plight of one animal to the awe-inspiring realization of a cosmos that embraces all possibilities, holding both joy and sorrow in its vast branching arms. This is not a theory of ambiguity, but of plenitude where nothing is ever unmade, only separated. This branching of all possibilities leads to one of the most unsettling and speculative ideas ever attached to the many worlds interpretation, a concept sometimes called quantum immortality. The thought experiment goes like this. Imagine a device is set up, linked to a quantum random number generator. It is programmed that if a specific, very unlikely quantum outcome occurs, the device will activate, resulting in a fatal outcome for a person connected to it. If the unlikely outcome does not occur, the person remains unharmed. According to many worlds, both outcomes happen, creating two branches. In one branch, the person's story ends. In the other, they survive. Now, ask a haunting question from the first-person, subjective point of view. Which branch does the conscious self experience? Proponents of this idea suggest that you, the observer, can only have a conscious experience in branches where you are alive to have it. Therefore, no matter how many times the lethal experiment is repeated, from your own subjective perspective, you would always find yourself in a branch where you survived through a miraculous sequence of unlikely quantum events. You would subjectively seem to cheat death indefinitely, not through magic, but through the statistical inevitability that there will always be at least one branch where your consciousness continues. It is a dizzying, almost ghoulish application of the theory, suggesting a form of immortality not of the soul, but of a branching stream of awareness. However, physicists who work on many worlds are nearly unanimous in rejecting this interpretation, and for very strong reasons. The first is a fundamental misunderstanding of probability. While it is true there will always be branches where you survive improbable events, the overwhelming majority of branches emerging from such an experiment are ones where you do not. Your conscious experience is not a ghost that flees from doomed branches into safe ones. At the moment of branching, copies of your consciousness are instantiated in all outcomes. The version of you that continues is not the same you that escaped. It is a new, separate instance that simply has memories leading up to a survival. The you in the fatal branch has an experience too, right up until its end point. To believe only the survivor's perspective counts is to mistakenly believe one branch is more real than the others, which violates the core premise of the theory where all branches are equally physical. Furthermore, consciousness is almost certainly not a separate entity that chooses a timeline. It is an emergent property of a physical brain. When that brain structure is disrupted, the conscious experience associated with that specific branch ends. The theory does not promise a singular self that jumps from body to body across the multiverse. It describes a vast proliferation of selves, each with its own finite story. The quantum immortality idea, while a provocative thought experiment, ultimately confuses a statistical curiosity about first-person experience with the actual, physical reality of the branching wave function. It is a reminder that even the most profound scientific ideas can be stretched into strange and personal territories where our intuition about self and survival struggles to keep pace with a cosmos of infinite copies. Such a breathtaking vision of reality inevitably runs into a wall of scientific skepticism. If we cannot see these other branches, if we cannot interact with them or measure them in any way, then is the many worlds interpretation truly a scientific theory at all, or is it just a fascinating piece of metaphysics? This is the central and most powerful criticism leveled against it, the problem of testability. At the heart of the scientific method is a simple principle. A theory must make predictions that can, in principle, be proven wrong. Since the other branches of the wave function are, by definition, causally disconnected from our own, we appear to have no way to detect them. They exist beyond the horizon of any possible experiment we could conduct from within this single thread of reality. This leads critics to argue that many worlds is not falsifiable, that it lives in the realm of untestable philosophy rather than empirical physics. It paints a majestic picture, but one that seems to hang on the wall, forever out of reach. How do its defenders respond to this seemingly fatal flaw? Their argument is subtle and turns the criticism on its head. They begin by agreeing on a key point. For any experiment you can design and perform within a single branch, the many worlds interpretation makes exactly the same predictions as the standard, collapse-based interpretations of quantum mechanics. It must because it is built from the same mathematical foundation. Whether you believe in a single collapsing universe or an endlessly branching one, your lab equipment will show the same interference patterns, the same probabilities, the same concrete results. The difference is not in the experimental outcome, but in the story we tell to explain it. Proponents then make a case for theoretical virtue. They argue that many worlds is actually more parsimonious, that it requires fewer unexplained assumptions. The standard interpretation needs to add the mysterious, undefined process of wave function collapse as an extra rule. It needs to draw a shaky line between the quantum and classical worlds. Many worlds, in contrast, simply takes the core quantum equation at its word and lets it run forever without adding anything new. In this view, the branching multiverse is not an extravagant addition, but the simplest and most logical consequence of the mathematics we already accept. The theory's strength, they say, lies not in making new predictions, but in providing a cleaner, more complete explanation for the predictions we already have. It removes the arbitrary and places the observer back into the system as a physical participant, not a magical cause. So where does this leave us? Is it physics or philosophy? The debate itself reveals a fascinating frontier in how we define science. For some, a theory that does not yield a unique, testable signature is not yet complete science. For others, the elegance and explanatory power of a framework, its ability to solve deep conceptual puzzles without contradiction, is a form of progress all its own. It becomes a matter of what we value more. A theory that tells us what will happen next in our lab, or a theory that also tries to tell us what reality fundamentally is. Perhaps the final test for many worlds will not come from peering into another branch, but from within, as we continue to probe the foundations of reality and ask whether our desire for a single, simple story is a guide to truth or a limitation of our perspective. The debate over what is truly simple lies at the heart of this scientific conflict. On one side stands the venerable principle of Occam's razor, the idea that the simplest explanation, the one with the fewest assumptions, is usually the best. At first glance, proposing an infinite number of universes seems like the most extravagant violation of this rule imaginable. It appears to multiply realities beyond all necessity, trading a single, if puzzling, cosmos for a boundless, teeming multiverse. How could such an immense ontological commitment ever be considered the simpler option? This is the gut reaction many have to the many worlds interpretation, and it is a powerful, intuitive critique. Yet the defenders of the theory offer a compelling counterargument. They insist that when you look under the hood, their model is actually the more parsimonious one. It all depends on what you are counting as an assumption. The standard interpretation of quantum mechanics, which requires wave function collapse, relies on two major additions that are not derived from its core equations. First, it needs the mysterious, instantaneous collapse itself, a process with no known physical mechanism. Second, it requires an undefined boundary, a line separating the quantum realm from the classical world, and it must define what qualifies as a measurement or an observer. Is it a conscious mind, a piece of laboratory equipment? The theory does not say. These are ad hoc rules added to make the mathematics match our experience. The many worlds interpretation, in stark contrast, proposes we take the central equation of quantum theory, the Schrödinger equation, at face value. It says, let this one elegant, continuous equation describe everything, from a single electron to a conscious human being to the entire cosmos. Do not stop it arbitrarily, do not add extra steps, just let it run. In this view, the branching multiverse is not an added assumption. It is the inevitable, logical consequence of the single mathematical rule we already accept. The simplicity, then, is not in the outcome, which is vast, but in the starting point, which is clean and uncluttered. It trades an infinite number of universes for the removal of two fundamental mysteries, the how and the why of collapse. So the debate becomes a philosophical one about the nature of simplicity itself. Is it simpler to have a single universe with extra, unexplained rules grafted onto it, or to have a single, seamless rule that generates a multiverse as a natural byproduct? One perspective values a sparse result, the other values a sparse set of laws. This tension forces us to question what we truly seek from a fundamental theory of reality, a comforting picture that matches our limited intuition, or a mathematically pure framework that challenges it to its core. This profound debate about simplicity leads us to an even deeper mystery, one that touches our most basic experience of reality, the relentless flow of time. Why does time move forward? The laws of physics at their most fundamental level are almost perfectly symmetric. They work just as well if time runs backward. Yet our lived experience is a one-way street, from an ordered past to a disordered future, governed by the increase of entropy. This is the arrow of time, and its origin has long been a puzzle. The many worlds interpretation offers a startling possibility that the direction of time we feel may be a direct consequence of the irreversible branching of the wave function. Think of decoherence, the process that separates branches. Once quantum information leaks out into the environment, it cannot be retrieved. It is a one-way trip. This creates a fundamental asymmetry, a before and after for every quantum event. In each newly formed branch, the local history becomes fixed, while the other possibilities recede forever. This perpetual, irreversible splitting may be the engine that drives our perception of time's arrow forward. Within any single branch, entropy increases, memories are formed, and causes always precede effects, simply because you are riding a current that only flows in one direction, the direction of perpetual branching. Yet here lies the beautiful and almost paradoxical twist. While every individual branch experiences the flow of time, the multiverse as a whole does not. From a God's eye view outside the system, the entire branching wave function is static. It simply is in a state of timeless perfection. All moments, all possibilities, all branches exist simultaneously in a vast, frozen structure sometimes called the quantum multiverse block. What we call the present is just our local position within this eternal structure, and our movement through it is an illusion created by our consciousness being locked to a single, forward-splitting thread. This suggests a profound link between the smallest quantum events and the largest cosmic scale. The branching that gives rise to alternative versions of you might also be the very mechanism that gives you a past to remember and a future to anticipate. It turns the arrow of time from a mysterious boundary condition of the universe into an emergent property, a side effect of the wave function's endless differentiation. We do not move through time. Time is what we call the experience of the multiverse endlessly elaborating itself. This perspective invites us to see our entire history, from the Big Bang to this very moment, not as a lone timeline, but as one intricate pathway in an infinite, timeless garden of forking paths. This branching logic does not stop at the edges of our laboratories or even our planet. It extends to the very fabric of the cosmos itself. When we scale the many worlds idea up to the grand stage of cosmology, we find it intertwines with our most ambitious theories of how the universe began. The leading model for the Big Bang's explosive first moments is called cosmic inflation, a period of faster-than-light expansion that smoothed and stretched the infant universe. Crucially, inflation is driven by a quantum field, and like all quantum things, it is subject to fluctuations, tiny ripples of possibility. According to inflationary cosmology, these quantum ripples were stretched to cosmic size, becoming the seeds for all the galaxies and vast cosmic structures we see today. But here is where the many worlds perspective adds a breathtaking new layer. If that primordial inflationary field was in a quantum superposition, then its fluctuations did not resolve into one single pattern. Instead, the universe branched at its very inception. In one branch, the quantum ripples created a specific arrangement of galaxies. In another branch, a slightly different pattern of ripples led to a completely different cosmic web. This suggests that the multiverse tree may have its roots not in a single Big Bang, but in a quantum event that spawned an infinite forest of universes, each with its own unique large-scale structure. This is the quantum multiverse, a cosmos where the first instance of time branched into every possible configuration of matter and energy on the grandest of scales. But the differences between these cosmic branches could be far more profound than just where the galaxies are. They might involve the very rules of reality. In modern physics, what we call the laws of nature and the constants of nature, like the strength of gravity or the mass of an electron, are not necessarily absolute. They may be determined by the state of underlying fields, often referred to as the vacuum state. Think of the vacuum not as pure emptiness, but as the lowest energy state of a field, like a ball resting at the bottom of a valley. Our universe exists in one specific valley with one set of physical laws, but the theoretical landscape of possibilities, especially in frameworks like string theory, contains an almost unimaginable number of such valleys, each with a different shape, representing a different vacuum state with different constants and potentially different laws. This is known as the string theory landscape. Now, combine this with the branching of the quantum wave function. During inflation, as the universe rapidly expanded, the quantum state of the inflationary field could have tunneled or fluctuated into different vacuum states in different regions. In the many worlds picture, each of these regions becomes its own separate, permanently disconnected branch of reality. This means that in the greater multiverse, there are not just branches where you made a different choice this morning. There are branches where the force of gravity is 1,000 times stronger, where atoms cannot form, where the concept of a star is impossible, or where time itself flows in a different manner. The fundamental rules of the game are different. This idea forces us to confront a profound and controversial question known as the anthropic principle. It observes that we, as conscious observers made of atoms and living around a stable star, can only find ourselves in a universe whose laws and constants allow for our existence. We are not observing a random universe, we are observing one that is bio-friendly, at least to us. In a multiverse where every possible set of laws is realized somewhere, it is no longer surprising that we exist in a universe fine-tuned for life. There will inevitably be branches that have the right conditions, and we, by necessity, are in one of them. This is not evidence for design, but a statistical inevitability in a cosmos of infinite variety. Our universe is not special because it is the only one. It is special to us because it is the one we can inhabit. This cosmological perspective transforms the many worlds interpretation from a story about particles in boxes into a grand narrative about the origin of all structure, all law, and perhaps even the very conditions that allow us to be here, wondering about it all. The theoretical landscape of the multiverse can feel impossibly distant, a philosophical abstraction. yet its fingerprints might be visible in a technology being built today, the quantum computer. This is not science fiction, but a real machine that operates by the very rules that suggest a branching reality. At its heart, a quantum computer uses quantum bits or qubits. Unlike a classical bit, which is definitively a 1 or a 0, a qubit can exist in a superposition, a blend of both states simultaneously. It is like a coin spinning in mid-air, not heads or tails, but both at once until it lands. By carefully choreographing these superpositions and their interactions, a quantum computer can explore a vast landscape of possible solutions to a problem all at the same time. When we run a calculation on such a machine, it feels as if we are tapping into a form of parallel processing that is exponentially more powerful than any conventional computer. But where is this processing actually happening? One compelling perspective, popular among many quantum information theorists, is that the computer is not just simulating multiple possibilities. It is briefly making them real. In this view, the superposition inside the quantum processor represents a genuine, if fleeting, branching of reality. Each possible computational path unfolds in its own branch of the wave function. The machine's final measurement then selects one of those branches, giving us a single answer, but that answer was found by leveraging the computational work done across countless parallel realities. It is as if you sent out an infinite number of copies of yourself to search a maze, and the one who found the exit reported back. This interpretation gives a startlingly concrete meaning to the power of quantum computing. Its advantage is not just about speed, it is about scope, accessing a multiversal workspace that exists within the fabric of quantum mechanics itself. While not every scientist working on quantum computers subscribes to this many-worlds view, it provides a powerful and intuitive narrative for why these machines are so fundamentally different. They are not just faster calculators, they are the first human-built devices that seem to consciously dance with the branching structure of reality, offering a tangible, working glimpse into the profound truth that our universe may be just one thread in an infinite computational tapestry. But if every version of you across the branches is equally real, where does that leave the unique, private world of your own thoughts? This question pushes us toward one of the most intimate and speculative corners of the multiverse debate, a variant known as the many minds interpretation. Here, the branching does not happen out there in the cosmos, but in here, within the confines of consciousness itself. This view accepts that there is a single, unbranching physical universe following the smooth quantum equations. In this one world, your physical brain, as a complex quantum system, can enter a superposition. When you observe a quantum event like Schrödinger's cat, your brain becomes entangled with the outcome. It physically holds both possibilities, the neural configuration for seeing a living cat and the configuration for seeing a loss, simultaneously. According to this idea, the branching is not of worlds but of subjective experiences. Each possible brain state gives rise to its own separate stream of consciousness, its own mind. So there is only one box, one cat, and one physical brain. But from that single brain, two entirely separate and unaware conscious experiences emerge, one perceiving each outcome. It is as if the single hardware of a computer is running two completely different software programs, each in its own isolated virtual space, unaware of the other. This interpretation is a dramatic attempt to localize the mystery. Standard many worlds multiplies the entire physical universe to explain our definite experience. Many minds keeps the physical universe singular and instead multiplies the interior, subjective realm. It suggests that the weirdness of quantum mechanics is not a property of reality at large, but a profound feature of conscious awareness itself. The branching is not a cosmic event but a personal one happening in the private theater of every observer's mind. This makes it even more speculative as it ventures into the hard problem of consciousness, an area where science still has few definitive answers. It asks us to believe that a single physical structure can give rise to multiple, disconnected subjective worlds. While this elegantly avoids creating infinite copies of planets and stars, it creates what some see as an even stranger ontology, an infinity of minds sprouting from individual brains. The theory remains a fascinating thought experiment, a reminder that when we probe the deepest nature of reality, we inevitably collide with the deepest mystery of all, the nature of our own experience. The many worlds interpretation is not the only contender in this quest to understand reality. It exists within a vibrant, unresolved debate, a landscape of rival ideas, each offering a different answer to the same quantum riddle. The oldest and most famous of these is the Copenhagen interpretation, named for the city where its principles were forged. This is the standard story taught in textbooks. It tells us that particles exist in a haze of probability until they are measured, at which point their wave function collapses into a single, definite outcome. The strength of Copenhagen is its pragmatic simplicity. It works perfectly for calculating what will happen in an experiment, but its weakness, as we have seen, is philosophical. It introduces a fundamental split in reality, a mysterious collapse with no physical mechanism, and it cannot clearly define what constitutes a measurement or an observer. It solves the measurement problem by declaring it a boundary of science, a place where our description simply stops. A radically different approach seeks to restore a classical sense of certainty. This is the pilot wave theory, also known as the de Broglie-Bohm interpretation. Here, there is no collapse because particles are not waves of probability. They are real, point-like objects with definite positions at all times, but they are guided by an invisible wave, a pilot wave that permeates all of space. Think of a surfer riding a wave. The surfer is the particle, always in one specific spot. The wave beneath them is the pilot wave, dictating their path. This theory is fully deterministic, meaning if you knew the exact positions of all particles and the shape of the pilot wave, you could predict the future with perfect accuracy. The randomness we see is due to our ignorance of the hidden details. Its strength is that it gives us a tangible, visual picture of quantum events, eliminating the paradox of superposition. Its major weakness is that it requires this invisible, non-local pilot wave that influences particles instantaneously across vast distances, a feature that feels to many like replacing one mystery with another. Then there are models that try to build collapse directly into the laws of physics. These are called objective collapse theories, with names like Garadi-Rimini-Weber or GRW. Their proposal is bold. The wave function does collapse, but it is not triggered by a conscious observer. Instead, it happens spontaneously and randomly, as a fundamental law of nature. In these models, every particle has a tiny but finite chance of spontaneously localizing at any moment. For a single electron, this chance is so small it would almost never happen. But for a macroscopic object, like a cat or a measurement device made of trillions of particles, the probability becomes a certainty within a fraction of a second. The measurement problem is solved by making collapse a real, physical process. The appeal is that it draws a clear line based on size or complexity, where the quantum world gives way to the classical. The challenge is that this new, spontaneous collapse process is an addition to quantum theory, not a consequence of it, and so far, no experiment has been able to detect its proposed effects. So where does this leave the many worlds interpretation? Each competitor makes a different trade. Copenhagen trades a clear mystery for practical results. Pilot wave trades invisible guidance for definite trajectories. Objective collapse trades a new law of nature for a clear transition. Many worlds trades an infinite multiverse for a single, elegant equation and the complete removal of collapse. It does not add anything new to the mathematics, it simply refuses to stop it. In this unresolved debate, your preference may depend on what you find more palatable, an infinite, branching reality, or a single reality with extra rules or hidden layers. This is not a sign of failure in physics, but a mark of its depth, showing that our best theories point toward a truth that is stranger and more wonderful than any one story can yet contain. The intellectual clash that gave birth to these ideas was not a minor academic disagreement, but a titanic struggle over the soul of reality itself. On one side stood Albert Einstein, the architect of relativity, who believed passionately in a universe that existed independently of our observation, a cosmos of definite, tangible objects governed by complete laws. He could not accept the inherent randomness and observer dependence of the Copenhagen interpretation. His famous objection that God does not play dice with the universe was a cry for a deeper, deterministic layer beneath the quantum probabilities. He sought a theory that described what is really there, not just what we might find when we look. Opposing him was Niels Bohr, the philosophical leader of the Copenhagen school, who argued that it was meaningless to speak of a reality beyond what we can measure. For Bohr, the wave function was not a description of an independent world, but a catalogue of our possible knowledge about it. The act of measurement was not a passive reveal, but an active participant in defining the phenomenon. Their debates, stretching across decades, were not merely about equations, but about the very nature of truth and the limits of human inquiry. Einstein fought for a realist view, a universe that is just there. Bohr championed an instrumentalist view where science is a tool for prediction, not a window into ultimate reality. This grand dispute seemed to end in a kind of stalemate, with Bohr's pragmatic approach becoming the working philosophy for generations of physicists. Yet the questions Einstein raised about completeness and objectivity never went away. They simmered beneath the surface of quantum theory like an unresolved chord. Into this unresolved tension stepped Hugh Everett. His many worlds interpretation can be seen as a startling attempt to synthesize the deepest concerns of both giants. It grants Einstein his wish for a complete, observer-independent reality. The wave function describes everything that is, a full and deterministic account of the entire cosmos, with no dice rolling needed. Every outcome is predetermined in the vast branching structure, yet it does this using the full, unadulterated mathematical formalism that Bohr insisted was complete. Everett took Bohr's own quantum machinery and ran with it to its logical extreme, removing the artificial stop sign of collapse that Bohr had placed in the path. In doing so, he created a vision that is profoundly realist, like Einstein wanted, but also profoundly weird in a way that might have unsettled them both. It suggests that the legacy of their dispute was not a victory for one side, but a signpost pointing toward a reality far grander and more strange than either could have conceived. The universe, it seems, may have found a way to satisfy both the dream of a complete description and the rule of quantum law, by simply becoming more than any single observer could ever hold. The legacy of that great debate is alive in physics departments today, where the many worlds interpretation remains one of the most passionately argued ideas in all of science. It is a theory with powerful, eloquent champions. Physicist David Deutsch, a pioneer in quantum computing, is a staunch advocate. He argues that the theory is not just plausible, but necessary for a coherent understanding of reality. For Deutsch, the branching multiverse is the only interpretation that takes quantum mechanics completely seriously, without adding extra, unexplained rules. He sees it as the simplest explanation in the truest sense, because it demands the least alteration to the core mathematics. Similarly, cosmologist Carroll makes a compelling case for its elegance. He points out that in our quest for fundamental laws, we should prefer theories that are precise and deterministic. Many worlds offers exactly that, a universe where the wave function evolves smoothly and predictably forever. There is no ambiguity, no special moment where the rules change. What we call randomness is just our lack of knowledge about which branch we are on. These supporters frame it not as a wild speculation, but as the most straightforward reading of the quantum textbooks already on our shelves. Yet for every prominent supporter, there are equally respected voices of deep skepticism. Nobel laureate Steven Weinberg acknowledged the theory's appeal but found its ontological extravagance, its commitment to infinite unseen realities, to be a fatal flaw. To critics, creating a new universe for every quantum dice roll seems like the opposite of simplicity, no matter how elegant the underlying equation. The philosopher of science Karl Popper's criterion of falsifiability is often invoked here. If we can never interact with or obtain any evidence from these other branches, they argue, then the theory steps outside the realm of empirical science and into the domain of metaphysics. It becomes a story we tell about the equations, rather than a description of something we can test. Renowned physicist Roger Penrose offers a different critique, suggesting that a true theory of quantum gravity will require a genuine, objective collapse process, one that many worlds deliberately avoid. For these detractors, the theory solves conceptual puzzles at too high a cost, populating reality with ghosts we are forever barred from meeting. This division is not a sign of weakness in physics, but a testament to its intellectual health. The many worlds interpretation is a serious minority view held by a significant portion of theoretical physicists and philosophers. Its very persistence highlights a profound and humbling truth that after a century of stunning success, quantum mechanics remains a theory whose deepest meaning is still up for grabs. There is no consensus on what it tells us about the nature of reality. This ongoing debate forces the entire field to confront foundational questions that are often set aside in the daily work of calculation and experiment. It reminds us that our most powerful scientific theories are not just tools for prediction, but invitations to a much larger conversation about existence, consciousness, and our place in the cosmos. The fact that brilliant minds can look at the same equations and see such wildly different pictures of the world is not a problem to be solved, but a mystery to be cherished, a frontier where science and philosophy meet. This unresolved scientific conversation has leaped far beyond the lecture hall, finding a vibrant second life in our stories and daydreams. The idea of the multiverse has become a powerful fixture in popular culture, a narrative tool that allows us to explore our deepest anxieties and desires. We see it in the classic structure of a choose-your-own-adventure book, where a single decision spins the reader into a different narrative branch, each with its own consequences. It fuels countless science fiction plots, from television shows exploring alternate histories to blockbuster films where heroes jump between realities to confront different versions of themselves. A recent and profound example is the film Everything Everywhere All at Once, which brilliantly uses the chaos of the multiverse as a backdrop for a deeply human story about family, regret, and the search for meaning in a universe of infinite possibilities. These cultural adaptations are fascinating, but they often reshape the scientific theory to serve a more emotional purpose. In most stories, the branching point is a conscious, monumental choice. A hero decides whether to take a job, accept a proposal, or fight a villain, and that deliberate act splits their world. This narrative device brilliantly explores themes of regret, destiny, and the paths not taken. It asks what our lives would be if we had made one different choice. The actual physics of the many worlds interpretation, however, is far more impersonal. The branching is not driven by our conscious, life-altering decisions, but by random, microscopic quantum events. The spin of an electron, the decay of an atom, a photon hitting a detector. These are the quiet, unseen forks that proliferate realities. In the true multiverse, there is a branch where you became an astronaut, not because you bravely chose to apply to the space program, but because a quantum fluctuation in a long-forgotten star altered a cosmic ray's path, which influenced a genetic mutation in an ancestor, which cascaded over millennia into a different set of circumstances that led you to a different career. The storybook version centers our agency, while the physical theory gently removes it, placing us in a cosmos where every possible version of our life unfolds from a foundation of fundamental chance. This distinction does not make the cultural stories any less valuable. They serve a different, equally important function. They give us a language and an emotional framework to grapple with the weight of possibility itself. They allow us to play with the dizzying concept that other versions of our lives are out there, to safely explore our fears of missed opportunities and our hopes for second chances. Science gives us the scaffold of the multiverse, but it is through art and story that we learn what it might feel like to live inside one. This cultural embrace reflects a universal human longing to see our choices and our very selves reflected in the grand architecture of reality, even if the universe itself operates on a different, more mysterious set of rules. This cultural embrace of the multiverse points toward a deeper, more personal question. If the many worlds interpretation were true, not just as a mathematical model, but as an actual description of reality, what would that mean for how we live our lives? The philosophical consequences reach into the very heart of our concepts of choice, responsibility, and meaning. Every time you face a decision, from the mundane to the monumental, the theory suggests that you do not choose one path over others. Instead, the universe branches to accommodate every possible version of that choice. In one reality, you took the job offer and moved across the country. In another, you turned it down and stayed. Both versions of you are equally real, each convinced they made a free choice. This presents a profound challenge to our sense of agency. If all outcomes are realized, does our deliberation matter? The answer from within any single branch is a resounding yes. Your conscious experience, your stream of memories and feelings, is inextricably linked to the choices made in your branch. The version of you reading this is the product of a specific chain of decisions, and your future will be shaped by the choices you make from this point forward. Your sense of responsibility is not diminished, it is localized. You are responsible for the well-being and consequences within your own thread of reality. The other versions are separate individuals now, living their own lives with their own burdens and joys. This perspective can be seen as both a comfort and a source of existential weight. On one hand, it suggests a form of cosmic forgiveness. Every regret, every missed opportunity is not lost. Somewhere in the vastness of the multiverse, another version of you seized that chance, mended that relationship, or found that happiness. The path you are on is not the only one where your essence finds expression. This can soften the sharp edges of remorse, offering a strange solace that no possibility is ever erased from existence. Yet the flip side of this coin can feel deeply unsettling. If every success is also guaranteed somewhere else, does that dilute the value of your own achievements? Is the graduation you worked for, the kindness you showed, the art you created, made less meaningful because in another branch you failed, you were cruel, or you never picked up a brush? This line of thinking can lead to a sense of vertigo, where individual effort seems to blur into a statistical inevitability. But this dread may stem from a misunderstanding of value. Meaning is not a finite resource to be divided among infinite copies. It is generated locally within the context of a lived experience. The joy you feel at a personal triumph is no less real because another version of you feels it too, just as the warmth of sunlight is not diminished because it shines on another person. Your story retains its unique significance because you are the one living it. The multiverse does not erase identity, it proliferates it. Each branch carries forward a consciousness that, from its own point of view, is the central character in an unrepeatable narrative. This framework also reshapes how we might view hardship. In a single universe theory, a tragic event is a unique and absolute loss. In the many worlds view, while the loss is utterly real and devastating within your branch, the larger structure of reality holds the memory of other possibilities, including branches where the tragedy was averted. This does not undo the pain of your experience, but it might, for some, place it within a context of unimaginable plenitude, where love and connection are never completely extinguished, only separated. Ultimately, the theory invites a shift from a mindset of scarcity to one of abundance when contemplating existence itself. It asks us to consider that our lives are not solitary threads dangling in a void, but rich patterns in an infinite tapestry, where every shade of human experience is woven into the whole. Whether that thought brings comfort or unease may be the most personal quantum measurement of all. The search for evidence may not require peering into another branch, but listening to the universe itself. One of the most promising frontiers for testing the deepest nature of reality lies in the quest for a theory of quantum gravity. Our two most successful descriptions of the cosmos, general relativity and quantum mechanics, are fundamentally at odds. General relativity paints a beautiful picture of space and time as a smooth, curving fabric, perfectly predicting the motion of planets and the bending of light around stars. Quantum mechanics, on the other hand, reveals a microscopic world of probability and uncertainty, where even the vacuum of space seethes with fleeting particles. These frameworks work flawlessly in their own domains, but they break down completely under extreme conditions, like at the center of a black hole or the very first moment of the Big Bang. To understand these realms, we need a single theory that unifies them, a set of rules that describes how gravity behaves when space and time themselves become quantum entities. This is the holy grail of modern physics, and its discovery could reshape our understanding of everything, including the validity of ideas like the many worlds interpretation. The path to this theory is being paved by listening to the cosmos in a whole new way. The detection of gravitational waves, ripples in the fabric of spacetime caused by cataclysmic events like colliding black holes, has opened a direct window into the most violent gravitational processes in the universe. These waves are a pure prediction of general relativity, but as our detectors become more and more sensitive, they may one day reveal subtle signatures that only a quantum theory of gravity can explain. For instance, some models suggest that the fabric of spacetime might not be perfectly smooth, but have a fundamental graininess at the tiniest scales, a quantum foam. While this foam would be far too small to see directly, its effects might subtly alter the way gravitational waves propagate over vast cosmic distances. Finding such an imprint would be revolutionary, offering our first experimental clue that spacetime itself has a quantum structure. Another profound idea emerging from quantum gravity research is the holographic principle. It suggests counterintuitively that all the information describing a three-dimensional volume of space can be encoded on its two-dimensional boundary, like a cosmic DVD where a three-dimensional movie is stored on a flat surface. This isn't just a mathematical curiosity. It implies that our experience of a three-dimensional world might be a kind of illusion, a projection from a deeper, more fundamental layer of reality where quantum information interacts. If true, this radically reshapes what we mean by reality itself. How would the branching of the many worlds multiverse manifest in such a holographic description? Would each branch be a separate projection, or are they all woven into a single, vast informational tapestry at the boundary? While we are far from answering that, the holographic principle demonstrates that the ultimate nature of reality, as revealed by quantum gravity, could be stranger than any interpretation we currently have. Even the faint afterglow of the Big Bang, the cosmic microwave background radiation that blankets the sky, might hold hidden clues. This ancient light has traveled for over 13 billion years, and its patterns are exquisitely detailed maps of the infant universe. Some theorists propose that if the universe underwent a quantum branching event in its earliest moments, perhaps during inflation, it might have left a faint statistical fingerprint in this radiation, an odd asymmetry or pattern that defies standard explanations. Finding such a signature would be extraordinarily difficult and its interpretation hotly debated, but it represents a tantalizing possibility that the seeds of the multiverse were sown at the dawn of time and left a trace we might one day decipher. These are not tests of the many worlds interpretation directly, but investigations into the foundational framework upon which it is built. If future discoveries in quantum gravity reveal a universe that is fundamentally singular and deterministic at its core, as the many worlds view requires, it would lend powerful indirect support. If they instead point toward spontaneous collapse or other mechanisms that break the unitary evolution of the wave function, it would challenge the theory's core premise. The journey to this evidence is long and uncertain, but it grounds our most speculative ideas in the hard soil of empirical science. We may never visit another branch, but by listening to the whispers of space-time and decoding the universe's oldest light, we might just hear the echo of its existence. This cosmic silence is one of the greatest mysteries we face, known as the Fermi paradox. If the universe is so vast and old, teeming with stars and planets, where is everybody? The eerie quiet of our galaxy seems to contradict the high probability of life arising elsewhere. Yet when we view this silence through the lens of the many worlds interpretation, the paradox takes on a startling new dimension. In an infinite multiverse, every possible outcome for the evolution of life and intelligence must occur somewhere on the branching tree. There are branches where life never sparked at all, branches where it flourished but never developed technology, and branches where civilizations rose to span the galaxy. Our particular branch, the one thread of reality we inhabit, appears to be one of the quiet ones. From this perspective, the great silence is not a universal condition, but a local feature of our specific cosmic neighborhood. It becomes less of a paradox and more of a statistical observation. We find ourselves in a branch where, for a complex cascade of reasons, we have yet to detect or be detected by another technological civilization. The unsettling quiet is not evidence that we are alone in existence, but that we are alone in this particular version of existence. The multiverse answers the Fermi paradox not by finding the aliens, but by explaining why we might not see them here. It suggests a cosmos of unimaginable variety, where the branches buzzing with interstellar communication are out there, but forever separated from us by the fundamental architecture of reality. This leads to an even more speculative thought. If a civilization became sufficiently advanced, mastering the quantum laws that govern the branching itself, could they develop a technology not for traveling between stars, but for traveling between branches? The idea seems like pure science fiction, yet it emerges naturally from the theory. In a reality where all possibilities are physically real, the ultimate frontier may not be spatial, but probabilistic. A truly transcendent intelligence might seek to navigate the multiversal tree, accessing the knowledge and resources of alternate histories. Perhaps the signatures of such a civilization would be undetectable to our current instruments, not because they are hiding in space, but because they operate in a layer of reality we cannot yet perceive. Their communications might not be radio waves or laser pulses, but subtle manipulations of quantum correlations that only make sense from a multiversal viewpoint. This reframes the entire search for extraterrestrial intelligence. We have been listening for signals across the vastness of space, but we might need to learn how to listen for echoes across the vastness of possibility. The profound silence we experience could mean we are truly alone in this branch, or it could be the quiet before a completely different kind of contact, one that requires us to first understand the deepest nature of the reality we share. The silence of the cosmos mirrors the quiet, unresolved questions at the heart of the theory itself. For all its elegance, the many worlds interpretation leaves several profound puzzles on the table, challenges that keep physicists up at night and ensure the idea remains a vibrant, unfinished frontier. One of the most significant is known as the preferred basis problem. It asks a deceptively simple question: what exactly defines the way the world splits? The mathematics of quantum mechanics allows for many different ways to describe a superposition. Think of a quantum coin spinning. You could describe it as a mix of heads and tails, but you could also describe it as a mix of other, more abstract states. So when does the branching produce a world with a definite cat that is alive and another with a cat that is not, instead of producing worlds where the cat is in some strange, blended condition? The theory needs a rule to pick out the familiar, classical states we actually observe from the infinite mathematical possibilities. This is where decoherence provides a powerful answer, showing how interaction with the environment naturally selects certain stable states as the branches. But even here, debates continue about whether this process is fully sufficient to explain why we perceive the world in the specific, tangible way we do. Then there is the enduring puzzle of probability. If every outcome happens, what does it mean to say one outcome is 70% likely and another 30%? We explored the idea of subjective probability, of more copies of you experiencing the more common result. But translating this intuitive picture into a rigorous, mathematical measure of existence for each branch is an active area of philosophical and technical work. How do we weight the branches to recover the exact probabilities that quantum mechanics predicts and that every experiment confirms? It is a puzzle that strikes at the theory's connection to the empirical world. Perhaps the greatest open question is how this framework connects to the other towering mystery of physics, quantum gravity. The many worlds interpretation relies on the smooth, continuous evolution of the wave function. Yet our best hints about quantum gravity, from black hole thermodynamics to the holographic principle, suggest that spacetime itself may be emergent from something more fundamental, and that information may have deep limits. Could a final theory of quantum gravity reveal a granularity or a mechanism that alters the very concept of unitary evolution? Finding a way to merge the branching multiverse with a quantum description of spacetime is perhaps the ultimate test. A successful union would be a monumental step toward a complete theory of reality, while a conflict could force a major revision of the many worlds picture itself. These are not shortcomings that invalidate the idea, but signposts for future discovery. They represent active, exciting lines of research where mathematicians, physicists, and philosophers are collaborating. The work involves refining our understanding of decoherence, developing new approaches to probability in branching structures, and searching for those subtle imprints in gravitational waves or the cosmic microwave background that might hint at a deeper architecture. The mystery is very much alive, a dynamic puzzle reminding us that our most audacious ideas about the cosmos are not endpoints, but invitations to look deeper. From a single, puzzling electron to an infinite, branching cosmos, this journey reveals a universe stranger than fiction. We began with a simple question: why does observation seem to change reality at the quantum level? The many worlds interpretation offers a breathtaking answer, not by adding new rules but by removing an old one. It dares to take the elegant equations of quantum mechanics at their word, allowing the wave function to evolve forever without mysterious collapses or arbitrary lines between the quantum and classical worlds. In doing so, it trades a single, puzzling universe for a multiverse of unimaginable plenitude, where every possibility finds a home in its own thread of reality. This is not science fantasy, but a serious, albeit unproven, attempt to resolve one of the deepest paradoxes in all of physics. Its power lies in its radical simplicity, reframing randomness as perspective and transforming the observer from a magical cause into a physical participant within a vast, branching story. The implications ripple through everything from the nature of time and the fine-tuning of our cosmos to the very essence of personal identity. It asks us to consider that our lives are not solitary paths, but rich patterns in an infinite tapestry where every choice, every chance, every version of ourselves is woven into the whole. Whether this vision brings comfort or unease is a deeply personal reflection. Does the idea of infinite copies diminish your unique story, or does it expand your sense of connection to a cosmos of boundless potential? The quest to understand quantum reality is far from over. Experiments probing the foundations of gravity and the echoes of the Big Bang may one day offer clues, steering us toward one interpretation or another. Until then, we are left with a set of dazzling possibilities, each painting a different picture of what is fundamentally real. This conversation between mathematics and meaning, between the laboratory and the limits of imagination, is one of the most thrilling adventures of the human mind. We encourage you to keep exploring, to question, and to decide for yourself which version of reality feels most true. If you enjoyed this journey to the edge of understanding, please like this video and subscribe for more deep dives into the mysteries of space, time, and existence. Your curiosity fuels this exploration. Thank you for watching.